Okay, so here we're continuing on with class 8, and we're going to do another example problem. This is video 3, and so the previous example that we did used SI units. We're really just using British gravitational, and maybe I made like a little figure here so it looks like we can kind of see the thing we're doing. So we have water this time, and it's flowing as shown. It got a velocity here at point 1 of 1 foot per second. It's got a position of 2 feet, and I guess, yeah, okay, here. And it's got 1 psi. It's going to be measured here on this gauge. And here at velocity 2 is 16 feet per second. And you can see that this thing is converging, so it makes sense that the velocity here is going to be less than the velocity right here, right? So the converging of the nozzle has increased the velocity. And the position, it has gone down. So it went from 2 feet to 1 feet. And we want to find out or predict maybe what this gauge is going to read. So I'm going to go ahead and look up what my the density of water. They didn't tell us the temperature of the water, so we could pretty much guess that it's going to be standard conditions. If not, you would ask somebody. So here at 60 degrees Fahrenheit, we're going to have a density of 1.94. So I'm going to write H2O here. You can't see what I'm writing, so we'll put that back up there. These are going to be slugs per cubic foot. All right, so we'll talk about in a second what would happen if we were going to use, instead of using this equation sheet with material properties, if we used what was in Sengel. While I'm here, I could just take this 1.94 and multiply it by gravity, but they did give us the specific weight, so I'm going to go ahead and write that down, 62.4 pounds per cubic foot. And so while we're on the topic here, let's take a look in our book for these properties. Now, you know, in Munson, they did some nice thing by putting all the material properties that we see in our equation sheet. Those are all actually located in the front cover, in the back cover, which is a nice feature of the book. But here we go. Here is Sengel from the 4th edition. I hope I'm not pronouncing his name wrong because it's got the C thing. I don't know what that does, but that's okay. I'm okay with not knowing some things. All right, so here's some material properties, and it's the appendix 2 there, which has the English units. So if we jump to, let's see, we want to have boiling and freezing properties. Now here's the properties of saturated water right here. And so they do have the density, and we were looking at 60 degrees so we can compare. And you see they have 62.36 pounds mass per cubic foot. So instead of slugs, they're using pounds mass. But let's just go ahead and say, well, all right, that's the, let's write that down. Right? So we have here, this is out of Munson's table, out of the table that we're using with our equation sheet. But like if we go to here, we'll see that H2O at T is equal to 60 degrees Fahrenheit is going to be equal to 62.36 pounds mass per cubic foot. Well, doesn't that sound familiar, right? So all you would need to do is just divide by 32.2 in order to get 1.94, right? There's going to be a slight difference here. So if you had 62 point, here, I'm going to teach you how to use my calculator. You go 62.36 and then hit enter, and then go 32.2 and divide, and you get 1.9366. And if you were going to be very, very specific, you could go 62.36 and go 32.17, and you might get a little closer even to 1.94. But one of the reasons why we're not going to answer with like a ton of sig figs is because you can see there's already a little bit of variation onto these things. If you were in a laboratory, you might want to be really careful in there, but the real life ain't a laboratory. All right, so on this problem, we're going to start out with writing down Bernoulli between points 1 and 2. So P1 plus 1/2 rho V1 squared plus gamma Z1 is equal to P2 plus 1/2 rho V2 squared plus gamma Z2. And we're going to check our units as we go along, just like we did in example 1, because we did that in SI, now we'll do it in this. So P1 is given to us as, so we're looking for P1, right? Yeah, we want to find P1. So sometimes it's a good idea just to write that down and remind yourself, what am I doing this for? What am I looking for? I'm looking for P1. So P1 plus 1/2 1.94, I'm going to write it here, slugs per cubic foot, times the velocity here is 1 foot per second, but squared, plus gamma, which is 62.4 pounds per cubic foot. That should equal P2, which is 1 psi, so pound per square inch. We're going to see that we're going to end up being working in feet, pound per feet. So we're going to have to go 144 inches squared per foot squared. So that's just 12 inches per foot squared right there, right? So you can see that we're going to have pounds per foot squared. We're running out of room here. I guess I'll come down to there. 1/2, 1.94. We don't need to continue with the units because we're going to check them right here in a second. And then 16 feet per second squared. And then lastly, we're going to go down to 1 foot. Did I do that wrong? I forgot to put in my feet right in there. Oh, my bad, sorry. I'm going to squeeze them in. Squeeze them in. So we started out at 2 feet. Yeah, I kind of squeezed it in, didn't I? Yeah, sure. And then this is going to be, let's put it in order. Let's put the gamma first, right? We got the gamma right there, so 62.4 and 1 foot. Okay. So first off, let me, I guess I'll get the in-between numbers. Let's see. Boom, right there. This guy is going to be 1.94 and just divided by 2, right? Because it's going to be multiplied by 1 right there, right? 1 squared. So what we get is 0.9700. We're going to find out later that this is sort of a type of energy. We can call it energy per volume. We can see based on the units. We'll talk about that in the next class just to try to hammer home what Bernoulli is actually an energy balance. But anyway, okay, so let's take a look at the units that are right here. We have a slug per foot squared, cubed, and it's multiplied by a foot squared over second squared. So one thing we want to look for when we're looking at converting units here is look for like an F equals MA so that we know that a pound is equal to a slug meter per second squared. So when we see that, what we could do here is we could turn this into a foot, right? That square. And so we take a slug and a foot and a second squared, and we can see that thing right there when we have, and I said meters. Oh, gosh. I'm so sorry. Feet per second, slug, foot per second squared. Maybe I should re-record this. No, I'm going to go with it. All right. So anytime you see that collection of a slug, a foot, and per second squared, you know that you're going to get yourself, boom, boom, that turns into a pound. You don't have to write this down here. This is something, a side note that I wanted to put in here. So, and then also that last foot gets rid of this, one of the 3 feet that are here that turns into a foot. So you know they have a pound per square foot, that this is pounds per square feet. This guy right here, you can see that he's going to be 62.4 times 2, so 124.8, which we should do in our heads, right? And you can see that that foot from that is going to get rid of one of these, so that's also pounds per square foot. And then over here, you can see that this is 144. You can see that this right here is, that's going to be the larger, probably one of the largest numbers that are right here. And so it's 16 squared times 1.94 divided by 2. So we have 248.3. And then lastly, obvious 62.4. So let's just write this out here, that P1 plus 0.9700 plus 124.8 is going to be equal to 248.3 plus, whoop, I left out my 144, didn't I? My bad, sorry. Put them in order, why not? 144 plus 248.3 plus 62.4. And from that, you get kind of a sense of what is driving this P1, which will turn out to be 329 pounds per square foot. And because that's not really the units we use for pressure most of the time, we'll divide by the 144 inches squared per foot squared and have it equal to 2.284 psi. And we can assume this is psig because it's a pretty low pressure right here. We're not talking about the right there, the absolute. But we're going to reflect a little bit onto what we're seeing here. This pressure at 1 is driving this thing to increase velocity down here. And because the velocity increased, the pressure drops from spot to spot. Also, there is some influence really between here and here of the gravity changing, right? So because this is more of a potential energy term, this guy right here. So the potential energy is higher here than it is down here. The kinetic energy, which is what this guy is right here, he's increased right here. But we could think of this sometimes. We think of this as strain energy, and this is really the push of the liquid pushing on one side with the pressure, that differential pressure. So it needs a pressure driver. So you can kind of see where that balance is coming from and what the contribution of them are. There's a lot of here. There is quite a bit of dynamic pressure. Kinetic energy is part of this. So this is the answer right there. And if we wanted to be really clear, we'll say that it's gauge because we've assumed that it is. Something I should have done in the beginning, but I probably just we can kind of we don't want to assume. We just want to double check. It has to obey this problem has to, in order to use Bernoulli, it has to obey the 4 rules, right? So it's along a streamline. I've drawn it along a streamline. It's kind of understood that it was. It's going to be incompressible, right? So the density remains the same here as there, and it's inviscid because there's no viscosity forces in taking place right here. And trying to think along a streamline, invisible. Incompressible, inviscid, and what else am I thinking of? Inviscid, incompressible, along a streamline, and boy, I hope I don't get an exam on this. That would be bad. No viscosity, steady flow. That's right, steady flow. Right. So nothing. This is not changing with time, right? So the properties of this spot are going to remain, including velocity, everything, we're going to remain the same here over time, and the same thing here. So the steady flow. Boy, I need to remember that one. So it is a cautionary tale, right? Try to remember all 4 of those things. Other things that there's no going to be temperature changes going on right there. You can almost think of it as a steady flow kind of quantity to the thing, maybe, or it's a steady state kind of thing. And then there's also no external work being added or subtracted, right? So there's no pump involved in here, and there's no turbine involved. So there you go. There's another example done. We're going to return with another example. Is that true? Yeah, one more. Okay.